The birth of Big Bang Theory. What if everything we know about our universe's beginning is incomplete? The Big Bang Theory has become the cornerstone of modern cosmology, but its origins were neither straightforward nor immediately accepted. Its development represents one of the most fascinating chapters in scientific history, where observation and theory collided with deeply held beliefs about the nature of our cosmos. The story begins in the 1920s when astronomer Edwin Hubble made a discovery that would fundamentally alter our understanding of the universe. Working at Mount Wilson Observatory with its 100-inch telescope, Hubble observed that distant galaxies were moving away from Earth, with more distant galaxies receding faster. This relationship, now known as Hubble's law, provided the first observational evidence of an expanding universe, similar to how raisin bread expands during baking. Each raisin, galaxy, moves away from every other raisin as the dough, space itself, expands. This expansion presented a profound implication. If the universe is expanding today, then running the clock backward means everything was once closer together. Follow this regression to its logical conclusion, and you arrive at a moment when all matter and energy occupied an incredibly dense, hot state, the birth of our universe. The scientific community initially resisted this idea. Einstein, whose general theory of relativity actually predicted an expanding universe, introduced a cosmological constant into his equations to maintain a static universe. When confronted with Hubble's evidence, Einstein reportedly called this addition his greatest blunder. This resistance wasn't merely technical. The concept of a universe with a definite beginning carried uncomfortable philosophical and theological implications for many scientists who preferred models of an eternal cosmos. Our cosmic models are deeply intertwined with our philosophical worldviews. While Hubble provided the observational foundation, Belgian priest and physicist Georges Lemaître developed the theoretical framework. In 1927, Lemaitre published a groundbreaking paper proposing what he called the primeval atom or cosmic egg hypothesis, the universe beginning as an incredibly dense point before expanding. Remarkably, Lemaitre published this theory 2 years before Hubble's evidence, deriving it mathematically from Einstein's equations. Lemaitre's work initially received little attention, partly because his original paper appeared in an obscure Belgian journal. When Einstein first heard Lemaitre's theory, he reportedly told him, "Your calculations are correct, but your physics is abominable." Yet as evidence mounted, skepticism gradually gave way to serious consideration. The term Big Bang originated from one of the theory's vocal critics. British astronomer Fred Hoyle, who championed the competing steady-state theory, coined the phrase during a 1949 BBC radio broadcast as a dismissive label. The catchy term ironically became the popular name for the model he opposed. Hoyle's steady-state theory proposed that the universe has always existed, with new matter continuously forming to maintain constant density as space expands, avoiding the need for a creation moment. The debate between these competing models continued for decades. The turning point came in 1965 with a serendipitous discovery by radio astronomers Arno Penzias and Robert Wilson at Bell Laboratories. While testing a sensitive microwave receiver, they detected persistent background noise coming equally from all directions, initially mistaking it for interference. They even checked for pigeon droppings on their antenna. They had inadvertently discovered the cosmic microwave background radiation, CMB. This faint radiation permeating all space was precisely what Big Bang theorists had predicted. If the universe began in an extremely hot, dense state, then as it expanded and cooled, the leftover radiation should still be detectable, albeit significantly cooled. The CMB provided compelling evidence that the universe had a beginning approximately 13.8 billion years ago. The scientific consensus shifted dramatically toward the Big Bang model. Subsequent observations strengthened its position, including measurements of light elements, like hydrogen, helium, and lithium in the early universe, which matched Big Bang predictions with remarkable accuracy. More precise measurements of the cosmic microwave background provided additional evidence. The COPE satellite in the early 1990s followed by WMAP and Planck missions, mapped tiny temperature fluctuations in the CMB that revealed the seeds of cosmic structure, fluctuations that ultimately led to galaxy formation. These observations confirmed the Big Bang model and provided detailed insights into the early universe. The standard Big Bang model explains a remarkable range of observed phenomena: the universe's expansion, the existence and properties of the cosmic microwave background, the abundance of light elements, and the formation of large-scale structures. Yet for all its explanatory power, the theory confronts a fundamental limitation. It cannot tell us what happened at time zero or what existed before. If we trace the expansion backward, our mathematics leads us to a point of infinite density and temperature called the initial singularity. At this moment, all known physics breaks down. The equations of general relativity produce nonsensical answers when applied to the singularity. The extreme conditions at the beginning require a theory combining gravity with quantum mechanics, something physicists have pursued for decades without full success. Even more perplexing is what triggered the Big Bang itself. What caused this cosmic explosion that created space, time, and everything we observe? If there was nothing before, no space, no time, then how did our universe come into being? These questions push us to the very limits of science, where observation and experiment become increasingly difficult, if not impossible.